Today we're going to be looking at taking the Adams-Bashforth method, which remember is a multi-step method that uses steps n and n minus 1 to move forward in time. And we're going to take that method and make it implicit, i.e. more numerically stable. And you recall that often that involves evaluating the right-hand side at step n plus 1. So we're going to construct a line using steps n and n plus 1 to extrapolate forward in time. And then we're going to end up with this so-called Adams-Moulton method, which is implicit method. Okay, so we're now moving on to our final multi-step method. And it's an implicit, so more numerically stable version of AB2 that we Adams-Bashforth 2 that we derived last time. And let me just write it down and then we'll derive it the same way. So Adams-Moulton 2, which is the implicit one, second order, plus delta t on 2, f of n plus f of n plus 1. So if you remember back to our implicit version of the forward Euler, on the left hand side we had n plus 1, but then we had f function evaluated at n plus 1. Okay, this is a little bit more terms here, but it's the same principle. Is we now have the right hand side has n plus 1 term. So it can no longer, it's not an explicit formula for n plus 1 in that sense, okay? And in general, when f is a complicated function, we can't necessarily rearrange it that easily. But it's more numerically stable. Certainly, we saw the example last time, so that's what it is. So basically, but the procedure for deriving it is very similar to Adams-Bashforth in that we're going to use the two values of function, but this time function n and n plus 1 instead of n and n minus 1 to construct a line, and then to use that to predict x n plus, to try to integrate the right hand side using the polynomial. Okay, so let's just draw the little diagram which is in the notes. It's not in the lecture notes, but it's quite easy to draw. It's just a simple extension. I can draw a straight line at this time. No alcohol has been consumed. N and n plus 1. So we have the function at step n now, and then the function at step n plus 1. So before we used n minus 1, but now we have n and n plus 1. And we use that to construct a line to then approximate the function on the right hand side so we integrate it. So that's our polynomial now. It's done in terms of those two values rather than the previous two values. So our polynomial is the function at the start point plus the gradient. So the gradient of this thing, again, let's write it down. Remember, that's delta t, that distance there. The gradient is f of n plus 1 minus f of n, all divided by delta t. So we have f of n plus 1 minus f of n on delta t, and it's now all times by our continuous variable, if you like, minus our starting point t of n. So that's really t of n. That's t of n plus 1 if you really want to be strict. It doesn't matter, it's step n. Okay. And we put brackets on. Okay, so that's the approximation. So that's the polynomial, the new polynomial approx of f on the right hand side. Let's go through the steps then. So let's just remind ourselves what we're trying to do. We've got dx by dt is our function f. We're integrating it from t of n to tn plus 1, like we did last time. So we do, the left hand side becomes dx by t, tn plus 1, t of n, which of course equals x at tn plus 1, tn, which equals x of n plus 1, x of n. Okay, so that's integrating the left-hand side. The right-hand side is integrating f dt, and we approximate that by between tn and tn plus 1 over one time step, and we're approximating that with our polynomial dt, tn plus 1, tn. So we substitute in our expression for the polynomial, and we have xn plus 1 minus x of n equals, let me use the new line, tn plus 1 t of n f of n plus 1 minus f of n on delta t times t minus t of n dt. Okay, so that's, and remember, for our purposes, just as before, we considered f of n plus 1 f of n. Of course, delta t is fixed, and t of n are all fixed, so the only thing that's varying is t. And we substitute again a dummy variable to make things easier. So it's t minus tn is, and then we know that ds equals dt. So we can just substitute in there, and then obviously we need to reevaluate s in light of its definition. So t, so that equals tm plus 1 minus tn on the top for s, and then tm minus tn on the bottom, which is 0. F of n plus f of n plus 1 minus f of n delta t, and then t minus tn simply goes to s, and that goes to ds. So it's a simple integral. Let's just write final line. But of course, tn plus minus tn plus 1 minus tn is simply the time step, so that's delta t. So this becomes a lot simpler. Actually, the algebra on this one is just slightly simpler than the Adams-Bashforth, I think. Same principles. So we're going to integrate up. That's going to give us a term. First term is going to give us a term in s. Second term is going to give us a term in s squared on 2. Right. So So the first term gives us s, and the second term gives us s, goes to the limits of delta t and 0. And then substitute those in, we get fn delta t plus fn plus 1 minus fn on delta t times delta t squared on 2. Now the delta t's cancel. Yeah, cancel there. We put it together, which implies that we then have xn plus 1 minus xn equals delta t on 2, and we have f of n plus 1 plus f of n. And then we look at, if we look at, oops, if we look at it finally, what we're doing intuitively makes sense as well, because we're basically approximating the function by averaging it between step n plus 1 and n. And so this is Adams-Moulton 2. AM2. Let's just write it at the beginning of the board and then talk a little bit more about it. Xn minus plus 1 minus xn equals delta t on 2 fn plus 1 plus f of n. So this is AM2, but it's also the trapezoidal implicit method that I mentioned earlier in the course, if you remember, if you look back through your notes. And now we have a rationale because we're using polynomials, so an order, for calling it calling trapezoid implicit second order. Because it's exactly the same scheme, or this idea of averaging the function. I mean, surely. Let me just look back in the notes of the form I gave you. Yes, which is exactly the same as the one. So in my lecture notes, that was page 28 of lecture notes. Okay, and we make that comparison. It's a second order method. And I think this would be a good time to actually stop. Now, actually, what I might, given I've got a few more minutes, let me just try and write down all the methods we've covered so far. So now we have covered a range of ODE methods, mainly for integrating in time. We started off with forward Euler, And we did implicit version or backward Euler. And each time we come across a method, we're trying to be as thorough as possible about analysing both its accuracy and stability. So even if you came across, which you did, came across forward Euler last year, you may not have appreciated quite in the depth, hopefully, that we've done this time, that it is first order and its different stability properties, both for decaying and oscillation. So we're going into more detail. So, and then we did leapfrog. And then we did our Runge-Kutta methods. And then we did our Adams methods. Okay, so depending on how you're counting, you've either got 5 or 6 or maybe even 7 different methods. So not a huge amount of methods, but that's a whole sort of pack of very common methods used in integrating ordinary differential equation methods. What we've done is we analysed the stability for these guys, numerical stability for the first bunch, and then we've done the accuracy issue for all of them, and that I think gives the right balance between complexity and principles. Of course, you can look out there and you will find analysis of stability of Runge-Kutta, and we'll use the same principles that we use for the numerical stability of the other things, like amplification factor and so on and so forth, equally for the Adams methods, and for oscillation. And if you're interested in looking at that further, I can give you some references for looking at extending the numerical stability into there. That knowledge does exist, it's just we're not covering it in this module. And then we've got the accuracy of all those. So that's quite a comprehensive. Given an ordinary differential equation that you won't be able to solve analytically now, you've got some methods for time stepping it to use comprehensively, and you should have now a much deeper understanding about their stability and accuracy. Okay, so underlying all these things were the two ideas, again, was stability on the one hand, numerical stability, and accuracy. And you have to have both to have a good numerical method. Okay, so on that point, I'll stop there. We have a couple more videos remaining then to look at, or maybe actually, yeah, one probably might take us to the beginning of the second half term, the first video of the second half of term, if we need be, on boundary value problems. So let me just talk briefly about that. So far we have time stepping problems, if you like. Of form dx by dt is f x comma t. But what about, and this requires an initial condition, often you have x as 0 at time equals 0 equals something, so these are sometimes also called initial value problems. And very common. But what about ones that have, you basically say e.g. have e.g. two boundary conditions? These are like dy by dx squared equals f of x, and then you have x of, sorry, y of x is 0 equals, and y equals x of 1 equals another value. And these are called boundary value problems. And it would be incomplete to cover just the initial value problems and not the boundary value problems at all. So that's what we're going to do next. We're not devoting nearly as much time to boundary value problems, but it will give you an insight. And actually this then blends hopefully quite neatly with the next big chunk of the module, which will be matrix problems, because to solve boundary value problems normally you need some sort of matrix inversion. So that fits together. Okay, so see you next time for more on that. Bye for now.